Yes, so thank you everyone for coming this evening to our second webinar of 2022. So this is on a nuclear physicist's guide to quantum computing. So you may have heard a lot about, quantum and qubits and quantum computers and quantum annealing and all the different types of, these type of terms. So Brent is going to be talking about what quantum computing is from a nuclear physicist's point of view. So we thank Brent for coming today to give us a talk. And he's from the Pacific Northwestern Lab of DOE. So this webinar is co-hosted by IEEE Computer Society Chicago. So we thank those members who are here tonight. So IEEE is basically kind of the sister organization to ACM. So they do very similar missions in terms of, conferences, in terms of publications, magazines, journals, and things like that, and also meetup groups. So we are the Chicago chapter of the IEEE Computer Society. We deal with topics of software, hardware computing, AI, big data, cloud computing, cybersecurity. And since the pandemic started, we've been doing a lot of these joint webinars together with ACM Chicago. So I'm the chair of IEEE Computer Society Chicago, and we have our website and our social media sites there, YouTube channel as well. So you can also be up to date with what we're doing. And of course, if you want to become an IEEE Computer Society member, you can also join there and get some particular discounts, on going to conferences and other types of benefits. Also, as well, we also have members from the Mid-America Club IT Connect group. So before the pandemic, we actually had our last meeting actually at Mid-America Club. So if you're not familiar, Mid-America Club is a business club. If you've gone to like the Aon building, the Aon Center, which is on Randolph, 100 East Randolph, then the top of that building on the 80th floor is the Mid-America Club. And we have an IT Connect group that talks about IT topics. And also because of the pandemic when it started, then we decided to join forces together to do joint webinars. So if there are members online this evening, thank you for your continued support of our webinars. We are planning to, when we go back in person, have events also too at Mid-America Club, because it's a great view of seeing a 360-degree view of Chicago. You can see Navy Pier, you can see the downtown. So it's really, and the river. So it's really, really great views and good for socializing. So the chair, who's also on the webinar, is Vijay Konkamala. He's one of the panelists there. And I'm the vice chair of that. And if you're interested in knowing more, you can Google us to see what we do. So we're a business club. We do networking, we do social events, but we're also a food and beverage club. So if you become a member, then you can be able to get really good membership fees and things like that for eating and for socializing. And of course, finally, those from ACM Chicago. So thank you for your continued support throughout this time and for last year's events and also for this year. So we are the Chicago chapter of the Association for Computing Machinery. So those people not familiar with ACM, it's like IEEE. We've been doing monthly meetings pretty much every year. I would say on par with that. I am the chair of the ACM Chicago since about 2 years ago. And vice chair is Mark Temkin, and our treasurer is Greg Newmark. And our events are on the Meetup site. So if you subscribe and you join Meetup, you can be able to find our latest or upcoming Meetup events there. We also have our social media sites, Facebook, Twitter, LinkedIn, YouTube. So we have a YouTube channel. So if you've missed any previous events, we have them recorded. Every webinar is recorded, and we post them onto the YouTube channel. So when you subscribe there, you will get a notification as to when the latest or the newest webinar event was recorded. And shameless plug, of course, if you want to become an ACM member, you can do so. You get discounts for going to ACM conferences and other types of stuff as well. Just a bit of housekeeping notes. So this webinar is being recorded, like I said. Everyone will get a copy of the link to the YouTube when it gets uploaded. The slides will also be provided also as well. So you don't have to, make screenshots or copy the information. And also as well, for those people that require a professional development hour for the certificate for getting a professional engineering, we will also provide the link to as well for that. So you can be able to claim this as part of your PDH. Okay, so with that, introductions. Tonight's presentation is Brent, and I'll now give it over to Mark to introduce Brent.
Hi, everyone. Thanks for coming. It's a great turnout. I want to mention before we get started that in addition to our Chicago following, we also want to thank those of you who are joining us through the other ACM meetups. I want to thank our speaker, Brent Van Devender, for being willing to speak tonight. I heard a podcast that Brent gave, and I knew that he would be a great speaker for our group. So let's have a big welcome for Brent Van Devender on A Nuclear Physicist's Guide to Quantum Computing.
Well, thank you very much for your kind invitation. All right, so first thing is to give you a little bit of my background. I am a nuclear physicist. I am possibly unqualified to talk to the Association for Computing Machinery about quantum computing, but I will anyway. There are actually quite a lot of intersections between our two fields, and that's what I'll focus my talk on. So the first thing we're going to have to do is tell you about my main research and what keeps me up at night. We'll talk about dark matter. We'll talk about neutrinos and the large scale structure of the cosmos. We'll talk about how quantum technologies related to quantum computing help me and my colleagues in that research. And then we'll find that there was, for me at least, a very fortuitous connection between my expertise and a particular need in quantum information technology. It has to do with superconducting quantum bits or qubits. And specifically, it's about the effects of natural environmental radiation on those devices. So most of the matter in our universe is dark. There's about 5 times more dark matter than what we can see in stars and galaxy. There are many independent pieces of evidence for it. You can actually see it. It leaves a special kind of imprint in what we call the cosmic microwave background radiation. The plot on the left is the temperature fluctuations of the microwave glow of the universe. More intuitively, you can see it on the right plot, and this is an image called the bullet cluster, where a cluster of galaxies has recently collided. It's a false color image. We're highlighting the dark matter in purple. So these galaxies have gone through each other. The dark matter just went right through without slowing down. We see that dark matter, by the way, through its gravitational effects. It acts like a lens on the galaxies behind it. And then in pink, we see the X-ray glow of the hot dust and gas. It's hot because it just scattered on another cluster of galaxies, and because it is normal matter, it drags, it's viscous, and so it slowed down when that happened, but the dark matter went right through. Whatever this dark matter is, it can't be normal matter that we know of. This is not protons, neutrons, and electrons. If it were, these galaxies couldn't have just gone right through each other like that. There are a lot of theoretical candidates for what they might be. They fall in 2 general categories we call particle-like dark matters. A leading candidate, you may have heard of WIMPs if you follow the field at all, weakly interacting massive particles. Or there's a category of what we call wave-like particles. An axion is an example of a particle that would satisfy those conditions. Like dark matter, our universe is replete with a subatomic particle called a neutrino. We at least know what a neutrino is. It is a really straightforward prediction of Big Bang cosmology, that the Big Bang will have created lots of neutrinos, so many that in the present universe, there are still 340 in every cubic centimeter. So like in the end of your thumb, there are literally 340 neutrinos there now. They're very light. In fact, in our particle physics theories, they are completely massless. We know at the most they weigh 1/billionth as much as a proton or a neutron. But because they're so abundant, they're a billion times more abundant than protons and neutrons. They might actually contribute a similar amount of normal matter to our universe. And if they do, they will have played a role in the evolution of large gravitational structures like galaxies and clusters of galaxies. This image on the left is a brand new galaxy survey from an instrument called the Dark Energy Spectroscopic Instrument. You're looking out into space. Every point in that image is a galaxy, and it's animated. And so what you're seeing is like a fan of galaxies, and then we're scanning that plane that you're looking in. The structures that I'm talking about, you can see, especially if you look down in the closer galaxies where the points are white, there are like clumps and clusters and filaments. Those are the structures I'm talking about. There's a very special imprint of dark matter and neutrinos possibly in those imprints. So we've been talking about matter in the universe and just taking it for granted, like it's just there, obviously. But the fact is, the laws of physics as we currently understand them can't explain how there's really any matter in the universe at all. As far as we know, the laws of physics are almost completely symmetric between matter and antimatter, such that these two things should have been created in equal amounts in the Big Bang and then almost immediately have annihilated, leaving us with just radiation in the universe. Of all the fundamental particles we know about, these neutrinos actually could offer us the way out. Because they're electrically neutral, unlike, say, electrons, they could be their own antimatter particle. Through that process, they can actually break the symmetry between antimatter and matter, giving us reactions in the early universe that would have favored the production of matter. The way to test that in the modern universe is to look for a very rare radioactive decay called Neutrinos double beta decay. So the pictures are on the left, a normal double beta decay, which is a well-known process. It's been observed where a heavy nucleus decay is giving you 2 electrons and 2 neutrinos emitted. But if neutrinos are their own antiparticle, there is also a possibility where that neutrino can be reabsorbed, like what is shown in the middle, such that all you see is the 2 electrons. If you observe this decay at any level, it's a sign that neutrinos have this special property and could be the way out of the origin of matter conundrum. So that's extremely important. It's actually one of the biggest efforts in the field of modern nuclear physics. It's an international effort to search for this rare decay event. Searches have been conducted in the past, coming up empty so far. They are able to set half-life sensitivities on this rare decay of at least 10 to the 25 to 10 to the 26 years. For reference, the universe is 10 to the 10 years old. And so we're talking about things that live on average longer than the universe. Now, you still have a chance of seeing these things decay because radioactive decay is random. Some of them will have happened, especially if you look at lots of material, because Avogadro's number is huge. And so the past experiments that set these limits have looked at like 10 to 100 kilograms of candidate isotopes for about a year at a time. The goal for the upcoming class of experiments we call the ton scale wants to increase that to 10 to the 28 years. Even with tons of material exposed for several years, we would expect to see only a few of these. And so it is really critical for us to control background events from environmental radiation, things like impurities in our detector materials, cosmic rays, and so on. We go to really extreme measures. Well, and to give you an example of the scale, we will have tons of materials exposed, and we can only tolerate something like 1 radioactive decay event per year per ton of material. And for reference, if you're not used to thinking about radiation, 1 fingerprint, if you get it on your detector, will give you 10 counts every year. And usually you put 5 fingerprints, not 1. So we can control this. It's a big part of what we do. We can design our experiments to be insensitive to the types of radiation we don't care about. We can select or even make our own materials to be very, very clean in a radioactive sense. And we also can add shielding including by going deep underground. So we'll go up to 2 kilometers underground. As an example of this, I'm showing you a picture of an experiment that some of my colleagues here at the lab are involved in called the Next Enrich Xenon Observatory, or NEXO for short. The plan for that experiment is to expose 5 tons of liquid xenon enriched in the isotope xenon-136 for several years, deep underground at a laboratory complex in Sudbury, Ontario. And among other things we do, besides going deep underground, we will grow our own copper. So this is one of our analytical chemists growing his own copper in such a way that we exclude like uranium and thorium radioactive components that are actually in almost everything. Light neutrinoless double beta decay, looking for dark matter, is you remember these galaxies went right through each other. So if they interact at all, they do so very rarely. But again, because Avogadro's number is huge, if we expose tons of material, we might see a few of these events on the scale of like ton years of exposure. The theory there is that some dark matter particle, here a WIMP called chi-naught in the upper left image, will scatter on a nucleus or an electron in a detector made out of, say, germanium. It can ionize the atoms, giving us charge that can be detected. It also sets the crystal lattice vibrating, creating phonons that we can detect. That's very rare, but here's in the middle, an example of a detector that some of my colleagues that do an experiment called the super cryogenic dark matter search, super CDMS. It's a germanium detector. This thing is, you could hold it in your hand. It's about this big, but there are many of these. And patterned on the surface of that germanium is a superconducting circuit, including, among other things, what we call transition edge sensors. So this is a kind of quantum sensor that can sense very, very weak signals. And what it does, the basic circuit of it is shown on the right. You operate the superconductor right at the temperature where it transitions between normal metal and superconductor. There's a very steep rise in resistance. So a small change in temperature on the x-axis results into a large change in resistance on the y-axis, and you can sense that with a type of amplifier called a squid. That's a superconducting quantum interference device. Like NEXO, super CDMS is also deep underground in the laboratory complex in Sudbury, Ontario. And I should say that this will come up later. In a superconducting circuit, the magic of a superconductor is at cold temperatures, the electrons pair up into what we call Cooper pairs. And it's that pairing of electrons that allows them to flow without electrical resistance. The breaking of those pairs is what converts it back to normal metal. And then this will come up again later in the talk. My own research specialty has to do with the mass of neutrinos. Remember, we talked about neutrinos, how much they actually do weigh determines what their imprint on the universe has been. You measure the mass of the neutrino with a technique we call it the Tritium endpoint method. Tritium is a radioactive form of hydrogen. We let it radioactively decay. It emits electrons. And by measuring the energy of electrons very precisely, we can infer the missing energy taken away by the mass of the neutrino. So if the neutrino has some mass m, we measure an energy E equals mc squared. And in this upper plot, you can see this shortfall in energy of the electrons taken away by the mass of the neutrino. Our proposed way of doing this is by having that tritium decay in a strong magnetic field that traps the electrons in the magnetic field such that they'll emit a very weak femtowatt, 10 to the minus 15 watt scale signal. We can detect that and use it to deduce the energy of that electron that we want with very high precision. But a femtowatt, that's a really weak signal, and we are really starved for signal to noise ratio there. And so for that reason, we once reached out to colleagues we know through collaborators at MIT who we know to have a type of quantum amplifier called a traveling wave parametric amplifier, or a TUPA for short. These are amplifiers that operate at what we call the standard quantum limit. That is the lowest possible noise consistent with the laws of quantum mechanics and irreducible fluctuations. If we could have those, we could really have a very low noise floor and a good signal to noise ratio. So we asked, could you make these to work for our application? The answer was yes, and they are actually doing that now, but that's a different story. What happened in talking to them about that, they heard about our problem, they're going to be able to help. They also told us about some of the problems they have. So what they do is use these amplifiers to read out their superconducting qubit devices. So very low noise, they operate in the right frequency range and so on. And so we're looking to consume quantum technologies for our physics research. And so we see what that quantum technology can do for us. But you can ask, is there anything we can give back? It's not at all obvious that the problems of quantum computing are nuclear in nature. But what they told us was everybody who operates superconducting qubit devices observes a phenomenon called quasi-particle poisoning. So quasi-particles are just the broken Cooper pairs of electrons in the superconducting circuits. You can think of them as just ordinary free electrons. By habit, I will almost always call them quasi-particles, but there's no difference that you care about. So quasi-particles are a really strong decoherence mechanism. They can cause your qubits to lose the state you prepared them in. There are far too many of them, orders of magnitude over theoretical expectations, and everybody sees it. It's independent really of the device details, when, where, and who does the experiments. It appears to be just a universal property of superconductors. Lots of people have ruled out sources, but one of the ones that was still out there having not been ruled out is that environmental radiation must be the thing propping up this population of quasi-particles. And so we're exposed to this hypothesis at the bottom of my slide that natural environmental radiation, cosmic rays, potassium, uranium, and thorium mostly, is breaking up the Cooper pairs and limiting the performance of superconducting devices. Now that's fortuitous because I just told you about the extreme measures people in my field go to control nuisance radiation. So when we heard this, it really seems like, gosh, I think we can help. So the main line of the story is to tell you about that connection. But to do that, now I've got to back up and actually start talking about quantum computing devices. So the first thing to talk about is quantum bits or qubits themselves and a critical performance metric called coherence time. So a qubit, unlike a classical bit that can only be in the states 0 or 1, a qubit can be in what's called a superposition of states 0 and 1. And there we get our first kind of magic of quantum computers, is that the amount of information contained in a qubit is just much more rich. And that's the first part of the power. It can actually be in any state, represented not just by the north and south pole, which are the 0 and 1 states, so those are perfectly fine states, but you can be in any superposition represented generically by a point on this sphere that we call the Bloch sphere. Operations done on qubits, like gate operations you would do for a quantum computing operation, are represented as rotations on the Bloch sphere. So for example, an x pi pulse means we rotate by pi radians about the x-axis. So if I apply that to the 0, I should rotate around to the 1 state. Or I could do the same, but only pi over 2 radians, and that would take a pure 0 state and put it on the equator in this superposition of 0 and 1 states. The coherence time refers to how long it can maintain that state before some unintended interaction with the environment wrecks it. So there are 2 ways you can fail in a qubit. There's what we call longitudinal relaxation. That's a type of error we call a bit flip error. That's analogous to classical errors, where you can just lose your orientation along the z-axis between 0 and 1. But you can also lose what we call the transverse relaxation, or a sign error, where you put yourself, say, on the equator, but maybe you drift around and don't stay exactly there. So 2 kinds of errors measured with 2 different parameters, T1 and T2. For example, though, the way to measure this T1 coherence time is quite simple. You measure what we call the polarization for the population. You put a 0 state into a 1 state with an x pi pulse, and then you wait some time tau and read it out and see if it's still in that 1 state. And you do that many times to build up an average, and you do it for different times, and you can map out a curve like this, and you can see that it exponentially decays. And we take the coherence time as the time it takes to get to 1 over E. It's about 1/3 of its original polarization. This particular device, this is real data, has a characteristic T1 time of 85 microseconds. And we'll do this measurement many times throughout this talk. So clearly we're going to have errors. We can prepare a 1 state, it will not stay a 1 state. So a couple of things. We want these qubits to stay in their state as long as possible. Tens to hundreds of microseconds is nowhere near long enough. But even still, they're going to have errors. And so we need to be able to correct those errors. So this is a thing. You can do it classically. The simplest scheme I know of for classical error correction is shown on the left, where you have one logical bit of information you want to store. You can simply do it redundantly by storing it on 3 physical bits. As long as the errors are relatively rare, such that you have at most one of them, you can then take a simple majority vote and reconstruct what your original state must have been, even in the presence of errors. So they have to be rare, so that there's only one, and they have to be uncorrelated, so that when one bit fails, it doesn't take another bit with it. If that happened in this 3-bit scheme, you would draw the wrong conclusion about what your original state was and not correctly reconstruct it. There are quantum analogies to this. The simplest one I know of takes actually 9 qubits to represent one logical bit of information. 9, because it takes 3 to protect, or there are 2 different errors, remember? It takes 3 to protect against the bit flips and 3 against the sign. And so you can, for instance, encode a 0 or a 1 state in these states that I've written out. You notice that they're in groups of 3. So qubits 0, 1, and 2 are in, first, they're in a superposition state. So they're in this mixed state of 0s and 1s. And I've added a new feature of quantum computers here. They're also entangled now. So if you look at the 3, 4, and 5 qubits, it's true for all the other groups too. When I make this measurement, what this notation means is if I measure those qubits, they're either all in the 0 state, or I'll find them all in the 1 state. So very roughly speaking, sign flips are protected by having the superpositions. The bit flips are protected by the entanglement. Like in the classical case, it's critical that these errors are relatively rare, such that only 1 qubit will fail during the time of one error correction cycle, and they have to be uncorrelated. This has to happen independently, or you'll reach the wrong conclusion. You won't be able to reconstruct the state that you had intended. So all that so far is generically true of any kind of qubit. Now I need to talk about a specific technological implementation of qubits. So I'll talk about superconducting qubits. There are a number of other candidates out there. They all have, well, all the superconducting ones have in common the presence of at least one structure called a Josephson junction. So a Josephson junction is just a structure where you have a superconductor, a very thin layer of insulator, like on the scale of a nanometer, and then another layer of superconductor. The Cooper pairs can then quantum mechanically tunnel through that insulator, giving rise to the special quantum mechanical effects. We characterize these qubits depending on what quantum mechanical observable is quantized in the circuit. They can either be the charge, what we call the magnetic flux, or the phase. As far as I know, virtually all modern qubits are a type of charged qubit called the transmon. All the ones I talk about will be like that. Now, the basic qubit circuit element here on the top right is you have the Josephson junction itself. It has some inherent inductance and capacitance denoted with the J subscripts, and then it's embedded in a larger circuit with external inductors and capacitors. If you know anything about electronics, then you immediately recognize this circuit as an oscillator. But it's a special kind of oscillator because the Josephson inductance is nonlinear. In quantum mechanics, if you just have a normal harmonic oscillator that you would get with normal inductors and capacitors, all of the energy levels have an equal spacing, and you can't independently control transitions between levels because all the transitions are the same. The nonlinearity of this Josephson junction breaks that degeneracy. Everybody has a unique transition now, and in particular, you can control transitions between the ground state, which will be the 0 of our qubit, and the first excited state, which will be the 1, without exciting any of those higher states. Just a couple of references for people that need the numbers. The frequency of these transitions tends to be a few gigahertz. That's kind of low microwave. And the energy is 10 microelectron volts. That's the typical energy difference between a ground and first excited state in qubit. So coherence times have been following Moore's law for a couple of decades now. This is the plot from a review that some of my colleagues wrote recently, and I have annotated here a world record that came after that. 300 microseconds T1 is about the best that's been done. It is the best that's been done. All these improvements follow from physical design of the devices, improvements in the quality of the materials, and so on. And that addresses, there's a whole host of decoherence mechanisms for a qubit. Many of them are denoted on the top plot on the top right. The one I'm talking about is what happens by excess quasi-particles. So down there in the bottom right. This one is particularly vexing, not in that we don't know what quasi-particles do when they tunnel through the Josephson Junction. We just don't understand why there are so many of them. But what they do is when they tunnel through, they can exchange energy, causing the qubit, like they can actually drive transitions of the qubit. And also, if you do a measurement that involves averaging, the number of quasi-particles that do that will tend to fluctuate, giving a rise to what we call a shot noise. Unlike most of the others, quasi-particles have a really particular kind of decoherence. If I write out in detail this polarization factor for a device dominated by quasi-particles, such as the one shown on the right, there are two factors. The rightmost exponential factor, this e to the minus t over t1r, that's kind of the normal exponential decoherence from all the other sources. But then the quasi-particles are this super exponential. If you look closely at the typesetting, that's an e to the minus t over t1 associated with quasi-particles. You can see that in the plot that this is actually a flux qubit. I said all mine were going to be charged. I lied. This is the one flux qubit dominated by quasi-particles. There's the normal exponential part out here at high times. It's a flat line on a log plot, but you see it kicks up. This is the low times are where you're dominated by quasi-particles. And whereas you might have expected a coherence time of 55 microseconds from normal sources, the coherence time of this device is actually more like 10, limited by the quasi-particles, which remember are just individual free electrons. I keep saying that there are more quasi-particles than what we expect from theory. We should talk about that. This is a pretty straightforward calculation of thermal physics to figure out how many broken Cooper pairs there ought to be in a superconductor. So that's this factor in subthermal. It consists of a few different factors. There's what we call a density of states. So, how many quasi-particles per unit energy and volume can we fit in the device? Delta is what we call the gap energy of the superconductor. This is like the binding energy of those electron pairs. Also, how much energy it takes to break them apart. That's 180 microelectron volts above the transition energy of the qubit itself. And then KT, K is Boltzmann's constant, T is a temperature. Typical temperatures are 20 millikelvins. KT, the mean thermal energy at that temperature, is 1.7 micro electron volts. And then there's this suppression factor, this e to the negative delta over KT, which gives you exponential suppression as the temperature goes down. Plugging in all the numbers, you find that the quasi-particles you expect just because of the temperature of the device is 10 to the minus 40 per cubic micron, which is like vanishingly small. That's basically none at all. The actual observations are 10 to the minus 2 to 10 to the 2, so hundredths to hundreds. And for reference, to get a density of 10 per cubic micron from thermal origin, you would have to turn up the temperature of your device to 165 millikelvin. That corresponds to an energy, though, that would drive transitions between the transitions of the qubit. So you have to be cold not to do that. So that's kind of a theoretical proof that these can't just be there because of thermal physics. There's also experimental observations that the quasi-particles in real devices are hot. This is work done by Kyle Cerniak and others with devices where they're actually able to see individual quasi-particle tunneling events. There are a few different kinds. There's what they call, there's interband, where they don't exchange energy at all. There's relaxation and excitation, where they exchange energy with the qubit such that you can drive a 0 to 1 or a 1 to 0 transition. They see that because it changes it's what we in quantum mechanics we call the parity of the states. Every time the relative charge on the islands in their device changes, the parity changes between the red and the blue in this middle plot. And you can see the difference between the ground state energy and the first excited state, which determines the operation frequency of the qubit, is very different depending on the parity. And so they can just watch these frequency changes and count. What they find is that the tunneling events are what you should see if there were just thermal quasi-particles, is that the relaxation should vastly outweigh the excitation. The cold quasi-particles just don't have enough energy to raise the level of the qubit. But the fact is that the excitation outweighs relaxation 3 to 1. And so they must be, I use hot in quotes, they're high energy. Thermal may not be the way to describe them. Their data for relaxation rates is shown in the plot on the upper right. A relaxation rate is just 1 over the coherence time. Sometimes it's convenient to use a relaxation rate. Their data, which are the points, don't match thermal expectations until they turn their device up to about 165 millikelvin or more. And remember, that's what I said you would have to do to get, to make a thermal population consistent with what you actually see. So I call this beyond BCS physics. BCS is the Bardeen-Cooper-Schrieffer theory of superconductors that predicts this. Whatever is making this, it is not normal superconducting physics and thermodynamics. We can see, not in qubits, but in resonators, our first potential connection to environmental radiation. So this is a work done by Cardani and others, who notably are neutrinos double beta decay people. Cardani and half of her co-authors are neutrinos double beta decay people. They took not qubits, but resonators. So these resonators are just simple superconducting strips on this device on the left. This is a false color image of the device. And I'm circling for you. Actually, they did it in their paper. Labels for the resonators A, B, and C. There's a ground plane, a superconductor on the back of this device. A strip of superconductor just sitting there will have an inherent inductance. And it has a component called the kinetic inductance, which it depends on how many broken Cooper pairs are in it. As the kinetic inductance changes, you're basically changing an inductor value in your resonator circuit. And so the resonant frequency changes. So by monitoring the resonant frequencies of these, they can see fluctuations in the numbers of quasi-particles. And so moving over to the plots on the right, there is at the top an overlay of several time series that they recorded. You can clearly see these bursts where the frequency drops quickly and then slowly over the scale of seconds returns back to normal. The average rate there is about 1 every 10 seconds, which is consistent with the rate of cosmic ray impacts on a device this size at the surface of the Earth. Importantly, and this will come up later, they are not independent among the resonators. So what the bottom plot is showing you is for frequency changes in the A resonator at the top of the device, what's the frequency change you see at the same time in the B and the C resonator further down. And you can see on that plot, it is not just random, there's a clear correlation. So if this is really cosmic rays hitting anywhere on the chip, they're tending to affect the devices everywhere on the chip. If it does this for resonators, it probably does it for qubits too. And you will recall, I told you that we need independent errors if we want our error correction schemes to work. So this is our first sign of really serious trouble. Well, our second sign, really. The first sign is that radiation is going to cause the faults at all. Same authors continued that work. That data was all taken on the surface. They also took their experiment deep underground to a mine in Italy called Gran Sasso and repeated the measurements And what I'm showing you, so you see a diagram on the left, they were 1.4 kilometers below a mountain. They monitored these resonators. And what you see in the bottom plot is there are two different experiments done at the surface, one round in Karlsruhe, one round in Rome, and then the round deep underground at Gran Sasso. I'm showing you the burst rate for all three resonators. And so for every group of three, you can see that the Gran Sasso number, that rate of burst, is much lower than the ones measured on the surface. That's a pretty clear implication that the association with cosmic rays was correct. Going deep underground, by the way, is the only way to meaningfully shield yourself from cosmic rays. So what's going on there? Let's talk about the microphysics a little bit. We have environmental radiation, either from cosmic rays or from naturally occurring radioactive material in the environment. These radiations are what we call ionized, and that means it's measured in energies of like kilo electron volts, keV and up. They enter into a device. Here's a mock-up of the device on the right. It's an aluminum superconductor. There's an aluminum oxide Josephson junction, all patterned on a silicon substrate. Those radiations can come in, ionize atoms either in the silicon or break pairs directly in the aluminum. Those ionized pairs, the electrons and the holes they leave behind, will recombine in a way that emits phonons and photons. Photons are just particles of light. Phonons are these lattice vibrations. Either one of those can diffuse throughout the device, eventually coupling their way into the aluminum superconductor, where down at the scale of like, milli eV and below, they still have enough energy to break these bound Cooper pairs into free electron quasi-particles, where they then cause all the troubles we've been talking about. And so the experiment that we designed with our colleagues that we initially reached out to about the amplifiers, we decided to really do this with qubits and definitively make the connection to radiation. So the first thing we did was we needed a radiation source. We took a piece of copper, a little disk of copper, and we activated it in the research reactor at MIT. That takes natural copper, which is mostly 63, and makes copper 64, which is radioactive. That's perfect. First, it's copper, so that when you put it near your qubit device, it still has the same electrical properties. You won't have disturbed the electrical environment, which is important. It's got a long enough half-life that you could make it, get it installed in your experiment, and cool down your refrigerator, which can take up to 24 hours, and still have enough activity left to watch it decay away to nothing, but short enough that it will decay in one experiment cycle. So we put it in the box with a qubit device. You can see the box. You can see the orientation of the copper source in it. It's a few millimeters above the qubit device itself. In this particular experiment, we have a chip with 2 qubits on it. They're labeled Q1 and Q2, and this is a false color image. We're making them blue and orange to match the color coding of data that we'll show later. So the crosses are the qubits themselves. These are transmon charged qubits. The squiggly traces are resonators used to couple them to a transmission line used to send in the control signals and also read out the states. We need to know the radiation in the environment of the experiment. So this experiment was done at our colleagues' lab at MIT. We sent to them a standard radiation detector. It's just a sodium iodide detector, and measured at the site of the experiment, like right at where the dill fridge was. It's a typical spectrum that you expect in a concrete building on the surface. The plot on the right is showing the energy spectrum of hits in the detector, and we clearly recognize the usual suspects. There's potassium-40, thorium and all of its decay chain daughters, and uranium and its decay chain daughters. You see the gamma rays from radioactivity in the main plot, and then the little inset in the bottom left is a much larger dynamic range where you can see cosmic rays going out to much, much higher energies. With that in hand, we can take the known radiation environment and use a tool that's standard in our field called GEANT4, which simulates the transport of radiation, includes effects like material shielding. So you actually get pretty good shielding just by being in a dilution refrigerator. and can help us estimate the doses to the device. And so we made two different estimates shown in the plots on the bottom right. We made two different ones because we actually aren't sure where the energy deposition matters. So maybe you can absorb energy from as far away as the copper box that the qubit device is mounted in. That's the larger plot, the blue one. Much more energy there, just because it's a bigger hunk of material. And then the red is a simulation of the energy spectrum of radiations absorbed just in the silicon qubit device itself. In this plot, in this simulation, we don't include effects of radioactive, what I call contamination of normal device materials. Those are actually, when you're sitting on the surface, those are negligible usually. We have a model to match the data. Remember, we're going to measure this polarization or population P. It's going to decay exponentially with some characteristic decay time gamma. Now, we might get a super exponential. That gamma might itself be a complicated function. But we're basically going to do that measurement. I said we're going to put the qubits in the one state, measure them sometime later, see if they're still in the one state, and we're just going to keep doing that until the copper dies away. That energy relaxation rate has two parts. There's a part gamma sub QP due to the quasi-particles, and then the gamma due to all the other ones. That's the normal exponential stuff. And we have a model for how the relaxation rate of quasi-particles should depend on the total power. There's this square root relation, depends on the frequency omega of the qubit and this unknown parameter A. Gamma other is all the other relaxation mechanisms. Oops, excuse me. Go back. The power has a few contributions. This is the total radiation power. P internal is stuff inside the fridge, like we didn't include it in our simulations, but there might really be potassium, uranium, thorium in the stuff in the fridge. External is the radiation from cosmic rays and the contaminants, mostly in the concrete in the building. And then P sub source is what we are adding from the copper 64 source. The two radiation parts are the external and the source. And then in the data, so I'm showing you the relaxation rate, which is 1 over the coherence time, over a period of almost 500 hours for which we monitored these qubits. So you can see the blue and orange data from qubits 1 and 2 in the top plot. Remember that each one of these points is a composite measurement. And so the inset is showing you the underlying data that goes into one of those composite measurements. If you look very closely at that inset, you can see that super exponential uptick at the very short times where we were clearly dominated by quasi-particles for a while. On the bottom, we're plotting the simulated power deposited into the chip as a function of time as the copper dies away. And then at longer times, there are some impurities. We also made some gold 198, which took many more days to die away. Clearly, you see the qubit performed very poorly in the early hours, came back to the normal over the course of about a week in perfect correlation with the power simulated. These two plots don't have quite the same shape because remember there's a square root relation between the power in the bottom and the decoherence in the top. Putting that all together, we can plot the relaxation rate, 1 over the coherence time, versus the total power into the device. We can use the high power data at the earliest times to get this unknown parameter A and project it back to where it intersects with the modeled natural environmental radiation dose to arrive at what we think the limiting coherence time due to radiation should be. And we find that if you solved all the other sources of decoherence and didn't do anything special to control the radiation, you're going to be limited to 3 to 4 milliseconds of coherence time. That's still orders of magnitude too short. Now, by the way, in these devices, the actual coherence times were more on the scale of 100 microseconds. And so some other mechanism is actually limiting the qubits more than the quasi-particles. I am running behind, and so I'm going to skip our second experiment, but I'll just quickly say that if you can add radiation and degrade their performance, you should be able to shield the devices from radiation and improve the performance. We did that experiment. We built a lead shield, put it around That's what's on this scissor lift sitting at the bottom. We can raise that lead shield up and put it around the dilution refrigerator. The qubits are right about the middle of that. This person standing here, by the way, is Will Oliver from MIT and Lincoln Laboratory. He is the person we reached out to about the amplifiers who originally got us onto this hypothesis. We did that. We did see an effect. It's small because radiation isn't the dominant effect for now, but we were able to show that if you took away all the other sources of decoherence and you shielded your qubits, you should actually be able to improve the coherence time at least to dozens of milliseconds. I feel like I should say, what is the dominant cause if it's not the quasi-particles? I'm going to come back to this plot I showed you before, the Moore's law, and let's talk about that world record coherence time. That's actually a materials thing. What this group did was they took a qubit that they had already high performance but made out of niobium superconductor and replaced the niobium with tantalum everywhere. The hypothesis is that niobium has a very complicated oxide that it can form on its surface. And in particular, the ground state of those oxides are very closely spaced with first excited states. It can tunnel between them. We call that a two-level system. And that effectively acts like a qubit itself. And it's a thing that can exchange energy with your qubit and cause it to collapse its state. And so their hypothesis is that by simplifying that oxide, they have increased the coherence time. What still remains is imperfections at the surfaces, basically materials imperfections at either the sapphire to tantalum interface or even within the tantalum itself. Those are shown in the bottom and upper right plots, respectively. So at this point, we've got clear correlation between the radiation and decoherence losses. We had talked about the need for uncorrelated errors. About the same time we were doing our work, another group was showing that errors are most definitely correlated when they come from radiation. And so what this paper by Weiland and others shows is that on a device with 4 qubits shown at the top, they see 2 different kinds of correlation. In the bottom plots, there is what we call a charging, where the charge state of these qubits is changing, likely due to radiation interactions within about 100 microns of the devices. You make electrons and holes, they can actually get collected on the charge ions of devices. That's a long time scan. All 4 of the devices here are color coded according to this legend in the upper left of the plot. And you can see if you look into those 2 zoomed areas, that the 2 nearest neighbor qubits are often correlated. They charge and discharge together, but you don't see qubits that are kind of across the chip from each other having this correlated charge. But what you do see is you can use one qubit as, say, a trigger. Like you can take this upper blue qubit, use the charge event as a trigger, and then ask what do the coherence times of all the other qubits on the chip do in correlation with that. And you see that in the bottom plot. So the top plot is a typical charging event. The bottom plot is an average of a bunch of coherence measurements taken in coincidence on the 2 chips, on the 2 qubits across the chip. And you can see that they have a spike in the plot is the relaxation rate. One more slide. So there's this demonstration. There's a larger demonstration of this done on a much larger device. This is a Google device called Sycamore. Sycamore has 52 qubits, of which they use 26 to show correlated errors. They refer to this as catastrophic correlated errors. So the plots show a time series of simultaneous errors on the chip. You can see in the middle plot, the black is what you would see if the errors were uncorrelated. You can clearly see a long, high error tail of correlated events. And then they show you also the time evolution of one of these, and you can actually start to learn about the microphysics. So in each one of these gray slices, 1, 2, 3, and 4, they actually show you the map of where the errors happen. And so going around these images in the bottom right, you start at time 1 before the event, very low error rate. You see a spike in errors around the middle right in 2. It grows in 3, and then very slowly comes back to normal at this late time, 10 milliseconds later at 4. So this is just, and again, the rate is totally consistent with cosmic rays at the surface for a device this size. So clearly we're having cosmic ray correlated errors. I'm going to skip this one if I'm out of time and just say to conclude what's to be done. So our colleagues are furiously working on the two-level system materials problem. We expect they will catch up to where radiation is the limit in 10 years or less if we don't do anything about it. And so for us who can deal with the radiation, we claim that the time is now to deal with this and get ready. I think that the long-term goal for superconducting qubits is that they just have to be resilient to quasi-particles. There needs to be a design such that you don't, or you're somehow resilient against the excess. But for now, the thing to do to try to understand that excess more and how they interact is to go to a shielded environment underground. We need to do controlled experiments in a low radiation environment. We are currently installing a refrigerator in an underground laboratory at P&L. That's shown in the left plot. There's about 40 meters of water equivalent overburden, gets you to about 1% of the cosmic rays you would see on the surface.
Okay, that's great. Thank you, Brent, for that wonderful insight on quantum computing. We have lots of questions.
First question is from Isaiah Brown. It is, doesn't everything in quantum mechanics have both particle-like and wave-like particles?
Absolutely, it does. And so when I was talking about the dark matter candidates earlier, different candidates, it is often more convenient to think about it one way or the other. The distinction, although they both have both properties, is which one is more convenient for the one you're talking about. So, and it comes down to the density of particles. If there are very few particles, like volumetrically, it's easier to think about them like particles. If they're very dense, it's easier to think of them as like a coherent wave.
Can those large underground neutrino detectors detect double beta decay?
Oh, yes, they absolutely do. In fact, we go to these great measures to control all those backgrounds that we don't want. And in most cases, the double beta decay that's irreducible. If you have that isotope, you can't get rid of it. And so you absolutely see that.
What is a sterile neutrino?
Okay, that is way beyond the scope of this talk. As far as we know, there are three what we call active neutrinos. There are a few pieces of experimental evidence out there in the world that would seem to imply that we need a fourth. And there are disagreements about the nature of that fourth one. Some of them are light, not much heavier than the neutrinos we know. Some of them can be quite heavy. In short, what it is there is a way that these neutrinos can oscillate and change into one of these sterols in a way that they're effectively lost to us.
Could neutrinos survive a crunch from a previous universe? Given the expansion of the universe and the weird qualities of time, could there be relics of previous universes in our own?
Oh my gosh, I have no idea. I'm not going to pretend to know what happened before the Big Bang and what might have come through that. I only know what would have happened starting in the instance after it.
Well, that's a lot of time anyway. Why is 5 not enough? Intuitively, it should provide sufficient redundancy. Can one qubit not be used to reference correct against two error types?
So to convince you of that, to work through the logic and the quantum mechanics, I would invite you to read Peter Shor's original paper that I cited. If you only have one qubit, or sorry, the question is 5. Why is 5 not enough? Well, I'd have to construct an example of why. I'm afraid I'm not going to be able to do that quickly on my feet for you. Maybe what I'll do is paste in here a link to that paper that you can go and read, which clearly explains why 9 is what you need. Sorry, that's a kind of a non-answer.
Okay. Someone wants to know, how can they get involved in the research along with someone like you who are working in quantum computing labs?
Oh, it depends a lot on who you are and where you are in your career. If you're young, still in school, the thing to do is go to school and study any one of a number of topics that are important for quantum computing, like all the big science, physics, chemistry, material science, electrical engineering, computer science, math. Do that as an undergraduate. Most big universities will have groups that you can get exposed to this kind of research in. And for sure, if you go to grad school, you can go to grad school and study this specifically. If you're older, the lab, we collaborate with universities, private businesses, other labs. You can reach out to me and talk about it.
If the bits are entangled, how do you limit the decoherence of a string of bits?
So again, I would have to refer you to details in the Shor paper. The way that algorithm actually works is you prepare those states like I showed. And then you use it's not a measurement you make on them. You use what's called another set of ancilla qubits to interfere with those. And you measure only your ancillas. With those, you can detect whether that decoherence has happened and restore it if it has.
Okay, and for our last question, what algorithm representational advantages does quantum computing over other traditional computing architectures?
Okay, so that's a great question. So first thing to know is that there are only certain kinds of algorithms for which you get what we call quantum advantage. The most well-known one, and as far as I know, the original one was by Peter Shor. Quantum computers are really good at factoring huge numbers, such that you could, if you had a general purpose fault tolerant quantum computer, you could defeat almost any known classical encryption scheme. Other algorithms have very well-known representations which give you quantum advantage. Fourier transforms is one, sorting lists is another, and so on. Another place where quantum algorithms really have an advantage is in like physics and chemistry calculations, where, if you think about doing these things numerically on a classical computer, you have to numerically represent complicated functions. It takes a lot of bits to do that. The fact is, on a quantum computer, the qubits behave just like the things you want to do calculations about. And so you can use far, far fewer qubits to do certain types of calculations in chemistry and physics. It is widely believed that the first major beneficiary of quantum computer, even in the era that we call noisy intermediate scale quantum, before we get to real fault tolerance, will be quantum chemistry calculations, effectively solving for where the electrons in complex molecules are. And it's because the qubits behave like the electrons themselves.
Thanks. And I know we have a lot more questions that piled in, but due to time constraints, we're going to move on from there. And let's have a big round. I know we can't hear it over our Zoom microphones for Brent. Great talk. And I certainly understand a lot more than this is not just the next computer chip. Tell you, we don't have the date for this yet, but coming soon, we have a digital currency presentation from the Federal Reserve Bank of Chicago coming up soon. And in fact, there is a possibility in the fall that we're going to have a talk from Microsoft Research on, let's say, their version of the movie The Intern. You can always visit our archive page where we have all of our videos. This presentation will be on the page as well. And you can go back and revisit all of the presentations that we've given since September of 2021. Very easy to just, if you put in ACM Chicago YouTube. And we're always looking for people. This is a great place to develop skills in writing, planning, videography, audio, and editing. We do, once we get these, I can't say how important this next one is, networking with future speakers and topics. If you're looking for, a lot of times we say, how do I get into a particular area? How do I meet people that are in that area? Well, this is a great way to do it. I've certainly met a lot of people that I wouldn't have done just by trying to answer ads for interviews. This is a way to do it. If you want to expand beyond your current scope, consider joining us and you'll get that experience. And of course, you'll help build interest in computing and computing related subjects. And finally, we're looking for speakers and topics, which could be you. Many times we've found people in the audience and we've asked them to be speakers. And sometimes we've had people that have volunteered to be speakers. And so don't think that your topic is too small or too uninteresting or that you can't do a presentation. That could be you.